Thank you. Thank you for giving me opportunity to talk about the activities within NRC in terms of passive removal materials for indoor air improvement. So I also want to start with the definition. The indoor passive removal materials are building and coating materials designed to improve indoor air quality with no or little energy input during operation. On the market, we already have a lot of them, including gypsum board, tiles, wallpapers, and paints. They are mostly based on Sorptive or photocatalytic oxidation process. So we NRC got interested into this material because the concept is great, but there were no or little information available for their performance beyond the claims by the manufacturer. So first goal our study was to develop a test protocol so we can produce some performance data in a standardized manner. The second goal is to evaluate the technology in a bigger scale, including room or house scale. So my former colleagues, Jeremy Sultan and Bob McGee, did a lot of work in terms of controlled chamber tests. Later, Mitra joined the group and she continued to work on this. And Mitra and I got involved in research house tests, and she and I will talk about this a little bit, and Mitra will finish the presentation for her modeling work. So in terms of facilities at NRC, to evaluate the passive removal products, we have a 400-liter chamber. This is just for a very controlled test in terms of temperature, relative humidity, and airflow. We can inject a single compounds as well as multiple compounds for this test. The second facility is called Indoor Air Research Laboratory. This laboratory consists of flexible modules so that we can have various configuration of rooms and size of rooms. Therefore, we can do side-by-side room tests in this facility. The third facility is a semi-detached twin research house, was built in 2018. Obviously, we can do side-by-side house comparison. And one of the houses has this passive material inside. So first topic is 400-liter chamber done by Bob and Jeremy. They tested 8 Sorptive materials and 3 photocatalytic oxidation materials. Some products were normal building materials and some of them are painted. And this PCO product were tested under UV and visible light. And here is the test condition. And this chamber is consists of inner and outer chamber. This inner chamber has screens and perforated plates upstream so that the airflow over the test specimen is very uniform. And we can inject the chemical from here and we measure the chemical inlet and outlet. So here is the example of the concentration. This from the 4-day absorption test and 3-day desorption test. This desorption test is to check whether the chemicals absorbed to test material would be re-emitted. So we use this data to calculate the removal rate of each product. Also, we can do this kind of we can apply this kind of mass balance model to back calculate the kinetic removal coefficient. So here are example of removal rates. It's very busy here, but two things are obvious. One is that the removal rate are all over the place. There's a wide range of removal rate, and the removal rate different for different chemicals. Here's the toluene and formaldehyde. So for toluene, the wallpaper impregnated activated carbon shows the biggest removal rate, but formaldehyde, the gypsum board shows the biggest emission rate, but removal rate. But as soon as the gypsum board was painted, the removal rate decreased a lot, sometimes 80%. So this graph is a similar thing for the PCO, and we did the 4-day test with the chemical injection and the 2-day test without chemical injection. Again, we calculated the removal rate here, and the product on the UV shows the most effectiveness, but sometimes some materials don't, the removal rate is very low. Also, it emitted various byproducts, including ozone and formaldehyde. So as I mentioned before, we have this research house, and there's 2 units that are exactly the same. So, but with a few differences. This unit E, east side unit has a structural material treated with coating to prevent mold growth, and the unit F, west side, has the passive panel. So we had the opportunity to go into the house and do the air quality measurement and ventilation measurement as well. So we used the 7-day passive method, meaning just you leave the sampling device for 7 days. So the sampling can be done passively. So original goal of this study was to actually validate this passive flux sampler that to determine the formaldehyde emission rate from different building materials, including floor, trim, and doors. So we use this opportunity to do the air quality monitoring as well. So you can see the passive flux sampler is working for door and the trim. And we also did the outdoor air quality monitoring here with the same passive method. And in terms of ventilation rate measurement, we use the 6 different fluoro-carbon tracer gases. The source is just a vial including liquid product, liquid chemical. So we deployed 6 of them for 1 each of floor. This is just to check whether there's any interzonal airflow between floors. And this shows the floor plan with the location of different samplers and the sources. So here are example of the trace gas concentration. So we'll find 2 things are weird. I told you that these 2 units are supposed to be similar or the same, but as you can see, the concentration are quite different. So something went wrong with this one. And also this MPDCH, this was deployed in unit E, but the concentration was high in unit F. So as you can see, there is some interzonal flow from unit E to unit F. So eventually we could do the 2-zone modeling. A 6th zone was not feasible because the concentration between floors were very similar to each other. So eventually the calculated ventilation rate was 0.05 per hour in unit F and 0.05 per hour in unit F. So there was about 10 times difference in terms of ventilation rate. So what happened is that the energy recovery ventilator in unit F was not functioning at the time. So this is the VOC and formaldehyde concentration. As you expected from the ventilation measurement, the concentration in unit F were about 10 times higher. But one exception, here's one exception. Formaldehyde level was similar, although it was a little bit higher. So as you can see, this passive material is working in unit F. So at 8 months, I went to the house again, but this time the ERB was working, but I turned off to repeat the test at 3 months. So we saw the exactly same thing. The ventilation rate was about 10 times lower in unit F, then the concentration was about 5 to 10 times higher in unit F. And here's another exception, formaldehyde. The concentration was similar. So this shows that the passive material in unit F was working for formaldehyde because it was designed to remove formaldehyde, but it was not working for other VOCs. So we can conclude that this passive material decreased the formaldehyde level by 3 to 4 times. And we can explain with this equation. So at steady state, the indoor concentration will be affected by outdoor concentration as well as indoor sources. And we measure the outdoor concentration and also the emission rate from each sources in the house. And if you consider this the removal rate by the passive panel, you can use this kind of coefficient back calculated from the 400-liter chamber. So if you do the modeling, this green is the measured one, and this blue is the predicted concentration without considering the removal rate. So as soon as you consider removal rate, the concentration would be the similar. So this shows indirect evidence that this removal material is working. And we can see the exactly the same thing from the 8-month observation. So can you generalize this? Probably not, because this is a very, very special case with very low ventilation, below 0.1 air exchange per hour. So if you go to very normal air exchange, like 0.3 and 0.5, we would get a more modest removal rate, like 30 or 50%. So it's been 3 years since I did this research, so I am looking forward to going back to the house and do the similar work, really side-by-side house comparison at the normal indoor ventilation rate. So now my colleague Mitra is going to present.
Hello everyone, this is a pleasure to be here and presenting the third topic of the NRC work, which is developing a model to evaluate the performance of passive removal materials. As my colleague Doyun explained, we at NRC have been involved in many different experimental work to measure the performance of passive removal materials during the past few years. The advantage of using experimental measurement, as you might be aware, is that this method is reliable, adequately describes the system, and provides the practical information from these materials. However, there are some disadvantages. For example, if you want to work in the lab scale chambers, it's mostly unrealistic condition that we have in these chambers, and for full scale, it would be expensive and time consuming. Next, please. Therefore, an alternative approach is considered to be simulation of these indoor air environment systems. So a computational fluid dynamic, or CFD, would be a powerful simulation tool that can help us to understand the concentration distribution, material performance, and the effect of environment when we use passive removal materials. Next, please. So we did our modeling based on two different phases, both phases including experiments and models in a small chamber and in the full scale environment. Next, please. So as Doyun mentioned, many different samples, including photocatalytic-based and sorptive-based materials, went through different tests: painted, unpainted, visible light, UV light, and I would like to add some other conditions that we tested, including change in the temperature between 20 to 28 degrees Celsius, change in the relative humidity between 30 to 75%, and test duration between 7 days to 28 days. And we evaluated the performance of many different passive removal materials, their removal efficiency, byproduct formation, and effect of these environmental conditions. Next, please. And at the end, we found that the highest removal efficiency would be for a sorptive ceiling tile, which demonstrated between 40 to 71% of removal performance for formaldehyde in different environmental conditions. Next, please. So based on these results from the experimental work that we had done, we kind of selected the performance, the passive removal material of interest for this method that we wanted to develop, and we used 400 chamber and find the sorption characteristics of this material as a function of operational parameters and the characteristics of the material itself. So the model that we developed for 400-liter chamber was a one-dimensional mathematical model, which is solved based on MATLAB. So next, please. So the information that we find based on the small chamber or 400-liter chamber that we have, we use it for the next step that would be the development of a CFD model using Conc. Here you can see a two side-by-side test room that has been designed and utilized for this purpose. There are two different two rooms, almost identical, with the total volume of 22.6 cubic meter for each. In one room, the sorptive ceiling tiles is installed, and the other room, the standard ceiling tile in order to compare the results from these tests. Next, please. So here are the instrumentation that we have considered for this test: a dyno calibrator to generate the formaldehyde source inside the rooms. And for the source of the formaldehyde, we use the formaldehyde perm tubes. Next. And we do samplings by the sampling pumps via HPLC sampling and also GCM MS sampling, the NPH cartridges, and 10x tubes. The duration of the sampling for HPLC would be 120 minutes, and for GCMS is 10 minutes. Next. So here, what we have done so far, as CFD modeling, we developed the model, and based on the injection of SF6, 6 cc per 10 seconds, in a room with displacement ventilation pattern, we validated the model. And after that, we just simulated the effect of ventilation pattern, including displacement, mixing ventilation, and overheaded mixing ventilation, in order to find the formaldehyde concentration distribution with and without the presence of passive removal materials. The source of formaldehyde we consider to be a wooden flooring with the emission rate of 49 microgram per square meter per hour. Next, please. And these are the concentration profile in the rooms based on the ventilation pattern. You can see the blue shows the lowest concentration, the red shows the highest concentration, and please note that the difference between the lowest concentration and highest concentration is between 8 to 16 microgram per cubic meter, so very, very low amount for all of them when we use passive removal material in the presence of ventilation pattern. The next one, please. And here is the profile from the upper view is for the breathing zone. Again, the distribution of formaldehyde inside the rooms based on different ventilation pattern. Next, please. So here you can see the result, a comparison between the effect, the performance when we have passive removal material and we don't have it. So no matter what kind of ventilation pattern we are using, it would be 38% up to 47% of improvement in removal performance of formaldehyde in the presence of passive removal materials. Next, please. We also did the health risk assessment using the recommended exposure limits for OEHHA, which is 9 microgram per cubic meter to be the in the safest level. And we can see again that for most of the ventilation patterns, it falls into the safe levels when we use passive removal materials. So as a conclusion, we can say that passive removal material has the potential to be replaced as a kind of IAQ improvement method and energy saving in built environment. So next one, please. For the future plan, we are planning to revisit, as Doyun mentioned, the side-by-side test houses under realistic condition, because there was a difference in the air exchange rate between the two rooms, almost 10 times difference. So the result wasn't very well comparable. So there is a consideration of going back to the rooms and doing the same test with the same air exchange rate for both rooms in order to have comparable results. And we have a lot to do with our model. We want to estimate the passive removal material lifetime, the effect of environmental condition and presence of different VOCs in the environment. And also we would like to validate the CFD model using a real source of formaldehyde in these rooms. Next, please. So these are the publications that we have had so far based on our work, and there are some more in their way. So, and there are some other reports, internal reports for NRC. Next, please. So if there is any questions or any suggestions or comments, we would be more than happy to be in contact with you or answer your question. Thank you very much for this opportunity.